Thank you very much. Good afternoon. Good afternoon. Much better. I always have to remember to ask, make sure everybody's awake. We just had coffee, so that's a good thing. So what I'm going to speak about for the next 40 minutes or so are some challenges that we have with very tall buildings from a fire safety perspective, but also to focus on a new SFPE guideline for fire safety in tall buildings. So Professor Sekizawa talked about many of the issues already. I'll talk a little bit more about those, but then spend more time talking about the SFPE guidelines and the general recommendations. So one of the reasons that we're focused on this is that many more tall buildings are being constructed around the world. And the building codes in most countries don't contemplate very tall or super tall buildings. In many countries, the definition of a high-rise building is somewhere around 23 meters from the access level to the top of the building. Some of these tall buildings are approaching 1,000 meters. So when you're looking at the difference between 23 and 1,000, fire department access, some of these other issues don't apply. You have to think differently about water supply, compartmentation, and so forth. So when the Society of Fire Protection Engineers started thinking about this, we didn't want to limit the discussion to those super tall buildings, so we generically left the title as tall buildings, because what constitutes a tall building with challenges to occupants and the fire service differs by country. But the principles about how to deal with them are very similar. So the guidelines that I will talk about was a partnership between the Society of Fire Protection Engineers and the International Code Council, which is the group that writes the model building codes in the US. So we very specifically didn't want this just to be an engineering perspective, but also to understand from a building code and fire code perspective what the issues are. So where I want to start is to talk a little bit about why we have some of these very tall buildings and we're seeing more and more of them. To start with, the rate of development in terms of building cities is increasing significantly. And if you look at the World Bank statistics in terms of how many people live in urban environments now and how many will be there in 20 years, the numbers are pretty staggering. So in a lot of countries, tall buildings are an option. That's also making the challenge that there's not an infinite amount of area to build upon, so building vertically is the response to that challenge. That means you're building taller buildings, you're putting more uses into that building, which makes it very complicated from a fire and life safety perspective. As we talked a little bit about before, there are some sustainability challenges too, because we have this global objective to reduce carbon emissions that is leading to climate change, but that means we're trying to design buildings more energy efficiently. So we're doing things like using natural ventilation instead of mechanical ventilation, which may work fine when you're dealing with a normal heating and cooling, but if you think of smoke exhaust through mechanical systems, if you take away the mechanical systems, you're taking away a mechanism for controlling the spread of smoke. And so you have to balance those types of objectives. We heard very well from Professor Sekizawa about challenges of the aging population. I'm sad to say Americans are not more fit as they get older. Unlike the Japanese, we're becoming less fit, more disabled. So that makes a much different challenge as we live longer and stay in our buildings. And I'll talk about some of these challenges and then some of the issues that we will need to consider as we look to tall building design into the future. So here's a picture of a not very highly populated area. There's some older buildings here, what we might call mid-rise buildings, some nice green space here. Does anybody have a guess as to where that might be? And when that might be? Nope. So this is Shanghai in 1990. So if we take that same view and we look 20 years later, you can see what we're talking about in terms of the rate of growth, densification, vertical construction, and the types of challenges that places on not only the city services, but in the case of fire, the fire service. You have a much different landscape in terms of accessing buildings with apparatus, getting inside of buildings. You have much more difficulty getting people out of buildings. And so all of these issues have to be taken into account in the design process, the management of the building, and planning for different types of events that could impact a building. So I had mentioned earlier that the World Bank and others have looked at the population growth, and 54% of the population now lives in urban environments. By 2045, that will increase by 1.5 times to a total of 6 billion people living in urban environments. So the population will increase by 2 billion in cities over that period of time. So the construction is not going to stop, and it's going to go much more vertical. And there are other benefits as well in terms of thinking about how the land might be used otherwise. Because if you take a plot of land that might have low-level housing and you put people in a high-rise building, now you have that space available, at least theoretically, for agriculture, to grow more food and to help sustain that growing population. So there's these types of trade-offs that have to be met that urban planners think about when they're looking at the vertical development. And we've all seen, the heights that some of these buildings are going to, and I very much appreciate Professor Sekizawa being able to go down 50 stories. If you're the occupant up here in the Burj Khalifa, you're probably going to be a little bit tired by the time you get to the bottom. And if everyone else is trying to use the stairs, then you have a capacity issue because the floor plate of the buildings is not that large, so you're limited in the number of stairs you have, and you have to think about how to use elevators to assist evacuation. So it's not that it's just a growing trend, it's a necessity. Because as we build these super high-rise buildings, there's really no other way to efficiently get in and out. And this will be a little bit difficult to read, but this is from there's an organization called the Council on Tall Buildings in the Urban Habitat, and this just shows the trend of number of buildings that would be considered super tall buildings over a number of years. So starting just in 1960 and really looking starting around the year 2000, it's an exponential growth in the number of buildings, and even looking at buildings over 200 and 300 meters in height, we're up around 1,000 buildings around the world at that level. So this is not a small problem. This is not a diminishing problem. It's going to be very much a growing problem. Another challenge, as I had mentioned, is that As we look at sustainability issues and trying to reduce energy, we look very much at buildings. And it's been discussed that cities and very much buildings consume close to 2/3 of the world's energy and account for more than 70% of the global emission of greenhouse gases. So that really drives this issue for reducing the power load in buildings. So reducing the heating, ventilation, and air conditioning, reducing the lighting, being more efficient, adding more thermal insulation and other measures. And that gives us different opportunities. For example, a double skin facade on the building, where now instead of just having the glass on the exterior, you have maybe a meter of space and another glass exterior, and the area in between is open, used for heating and cooling the air naturally in the tall building. And in concept, it works well, and for energy efficiency, it works well. But now we've just created an unmitigated path for fire and smoke. We spend a lot of time trying to make sure that we encase stairwells, elevators, mechanical shafts inside of the building. Now we're adding them to the exterior, which could create new problems. We're adding more insulation. This is an issue of the Grenfell Tower, and I'll talk a little bit about that. But as Professor Sekizawa said, as we're becoming more energy efficient, people are looking for ways to better insulate buildings. And because a large number of our building stock is existing buildings, the most efficient way to energy retrofit is to put insulation on the facade. So if you're using combustible facade material and combustible insulation, now you're creating a new type of fire threat that in tall buildings is quite significant. I already talked a little bit about natural ventilation, but another challenge is reduced material. So one of the sustainability concerns is that we want to reduce the amount of material we use from extracting raw material, processing, shipping to the site, use in the building, and recycling, the life cycle. And if we think about that, that translates into things such as optimizing or reducing the size of structural systems. So your steel member gets to be a little smaller. You use high-strength, lightweight concrete, which is less material. And that can be good, but then it's more susceptible to fire if the fire protection fails. And if we think about high-strength, lightweight concrete, that spalls more explosively than traditional concrete because the pore size is smaller and you have bigger issues. So if you don't have some additives such as fibers, carbon fibers, steel fibers, or other in that concrete mixture, you could have a more serious failure of that type of high-strength concrete than you would under normal weight concrete. Other issues are that we're trying to push alternative energy sources, and we're putting photovoltaic panels on buildings. That's great, but we have to remember it's generating electricity. It's a source of ignition. So when we start to think about we're putting an ignition source on a building that we just insulated with more combustible insulation, we're starting to build effects that could be very concerning. And part of the challenge is that the environmental focus doesn't think about fire safety. We have a history of disciplines working in silos, separated from each other. So urban planners, architects, engineers, and then even in the engineering, structural engineers, fire, mechanical. And if people aren't really talking to each other, we set up this challenge of having competing objectives, and sometimes you're going to lose a particular feature or function of a building, and it could be a safety issue. But that's a whole nother discussion for another day. Very quickly, here's just another indication of what Professor Sekizawa was talking about, of how quickly population age is increasing. These are US statistics from a few years ago. And the lighter colored numbers are the percentage of people 85 years and older. And so if you look from 1950 to 2000 to 2050, there's a significant growth in the percentage of people over 85 using buildings, staying in their home, going into public buildings, and the fitness and the abilities of people change over time. Here are some Japanese data that Sekizawa showed us already in terms of the changing nature of the population, which needs to be considered when you're thinking about egress time, protection in place, and factors such as that. Hopefully, you don't have the same problem as the US when it comes to obesity or being overweight, but this is numbers looking from 1985 when the Center for Disease Control started looking at, what percentage of people were obese or overweight in different states. So white was when they had no data, light blue is less than 10%, and it increases to where the dark orange brown color is more than 30% of the population in the state is obese. So if you look from 85 to 1995 to 2005 to 2010, most of the US, by medical definition, is overweight. And if you're overweight, that leads to health problems. It leads to problems with walking, with respiration. So those are all factors that you need to think about if you are trying to assess how quickly someone will be evacuating a building. And I see many engineers go look at data that were collected in the 1970s and assume that the walking speed and the fitness of that population group matches the fitness of the population group of today. And we really should be thinking about the population group 20 or 50 years from now, because we're not building buildings for one day. We're expecting buildings to last for 50 or 100 years. And if we're not looking at statistics like the aging trend, the obesity trend, the disability trend, we're going to have more problems into the future. So we always should be looking ahead in terms of what the demographics are in the building. So for these and many other reasons, the Society of Fire Protection Engineers thought it would be very helpful to develop a set of guidelines that talked about issues of fire safety in tall buildings. And the intent was not to be a very specific design guide telling you exactly what you have to do, because that's impossible. It's going to change by building, by country, and by a variety of factors. But it was really important, we thought, to highlight issues that are critical to think about when you're designing very tall buildings where you rely on the vertical systems to evacuate people, to get the fire service in, and you have challenges with the infrastructure that you have to deal with as well. So I won't talk about the historical fires. Professor Sekizawa did a very good job of that. But we unfortunately have very good examples of what not to do in buildings. The problem is we seem to keep repeating some of those problems. So even though we understand them, we seem to have a problem in repeating. One of the challenges that we have today that we didn't have as much a few years ago is this issue of exterior facade fires. So we started to see quite a bit of them in the Middle East region maybe about 5 years ago, and we saw quite a few in China as well. We've had some in the US, we had some in Australia, as I pointed out also this morning, but it wasn't until the Grenfell fire that people in countries that thought they knew what they were doing really realized that there was a major problem with putting combustible exterior facades onto buildings. So I'll talk more about that in a few minutes. But other issues, the elevator operation, and Sekizawa talked about that. We know we need to use elevators to move people in and out of buildings, but when you're 800 meters or 1,000 meters and you need to move people, how does that system have to work? How do you have to protect the shaft? How do you deal structurally with not having too much movement in the building so that you don't get the elevator off of its pathway? Structural fire resistance becomes a big issue because you're not going to be able to effectively fight a fire 50 stories, 80 stories above ground. You need that structure to be able to withstand the expected fire. Now, of course, we want to have and think about sprinkler protection, but water supplies in very tall buildings are also an issue. So here's a little graphic of the type of challenge or the type of solution that's sometimes used where there's reservoirs built in at various points in the building where the water is pumped up to those reservoirs in normal time so that you're not relying on the pumps and the water system in the emergency, and you have gravity feed to help you. But you have multiple redundant systems and different types of strategies that you need to think about in the fact that you don't want to be in a situation with no water in that tall building when you have no other way to get there. And Sekizawa talked about egress, and it's the same issue for firefighter access. I think it's good to put in firefighter elevators, but how many? For what capacity? Where does the equipment need to be located? Do you need air recharge stations inside of the building? If it takes you 20 minutes to get to the floor of the fire and you have a 30, 45-minute or even a 60-minute tank, you'll just get into the building and you have to turn around and get out. So building in these air recharge and other factors become really important in these tall buildings. And we'll talk about some of the facade issues and more as we go along. So these were all seen as issues that we wanted to somehow address in the guidelines. In addition, there's also the challenge of local availability of materials and components. And I was talking with some people about this earlier. There's often the idea that you can look at what another country is doing, look at what their standards are, look at what the equipment is, but are you going to get that same equipment into your country? Do you have the same level of installation and maintenance standards? Do you expect things to work in the same way? It can be very difficult to adopt a standard from another country that assumes a certain level of technology, maintenance, knowledge, performance, but if you don't have that where you're implementing it, it can be a problem. The local infrastructure is similar. That's your electrical grid, that's your water supply system, all of these other factors. In some of the Chinese cities, and particularly in some of the Middle East cities where they're building cities in the desert, you really have to think ahead about putting all that infrastructure in and then having a reliable power system. If you don't have a reliable electrical system and you build a super tall building and you're relying on elevators for evacuation and you don't have power, what are you going to do to get people out of 100, 150 stories? They will walk down the stairs. But that doesn't make it very easy for anyone going up in terms of dealing with an event. There's also the issue that, unfortunately, some of these buildings are very iconic, which is good, but it also means they might become a target for some type of terrorist activity. So you're not only thinking about the fire as an accidental event, you have to think about what could be other types of issues that would impact the building. So when we were developing the guideline, we took the approach that the only way to really do this was to take a performance-based approach. And so the guidelines assume that you're following something like the SFP guideline for performance-based fire protection or similar, that runs through a process of looking at your goals and objectives, performance criteria, design fire scenarios, and so forth. So I won't go through that process in detail. Again, that's a discussion for another day, but it's important because instead of just assuming that the regulations will address all of the situations of concern, you should be really thinking about the different issues and go through a hazard assessment, a risk assessment, understand the objectives you're trying to achieve with the building, what the concerns are, and go through a very structured process to do the analysis. So we start the process with a hazard and risk assessment. And when you're dealing with very tall buildings, it's not just fire. Unfortunately, we may have to think of terrorism, but also infrastructure, as I said before, the power grid going out or water issues, weather conditions in terms of very high wind, drought conditions, and others. So a tall building with a power outage is a big problem for all the people that live there. So cities have to think about that, not just in terms of the fire safety, but in the ability of the people. And you have to think about what additional measures you might need to put in that building for life safety systems to effectively get people out in the event of a fire. We recommend that a risk and reliability analysis be undertaken on the different systems within the building. So that's, for example, doing a fault tree analysis of what the different failure modes might be in your water supply system, your power system, your sprinkler system, your smoke control system, all of these areas to understand, is there any opportunity for what we call a single point of failure, where if you lose a critical system or component, you lose the capacity of that protection measure. An example of that would be a water supply system for a sprinkler in a tall building. If you have a single riser, single hydrant system going up the building, and you have an event that causes you to lose that riser, now you have no sprinkler protection in the building. And there was a very good example of that, perhaps a bad example, the World Trade Center bombing from 1993. So in 1993, the terrorists put a truck bomb in the parking area below the World Trade Center, which happened to be near the shaft which carried the communications and the power up the entire tower complex. So when they destroyed that, when they set off that bomb, you lost the fire alarm system, you lost emergency power, you lost communication. And in the end of the day, it took about 4 hours to completely evacuate both towers, in part because nobody had information. Nobody knew what to do. People were trying to get information any way they could. Some of the bosses in the companies were telling people to stay, others were telling them to leave, and it was just a very difficult situation. And so some people don't realize that because of that 1993 event and changes made to the World Trade Center prior to 2001, that really allowed so many people to get out of the building, so that even though we lost more than 3,000 people, it would have been much worse if we hadn't have had the 1993 event and made some significant changes to the building. So we always have to go through this learning process, but we have to really think about, what could fail and cause a problem. Then we look at what that problem is in terms of the fire, and we develop event trees that look at scenarios for both how the fire could spread and how big it could be if you have these failure points, but also what the impact might be in terms of getting people out of the building. So we tell people that this is required. We don't give a lot of detail, but we also point to, for example, the SFP Handbook of Fire Protection Engineering, which has several chapters on risk and reliability analysis. As Professor Sekizawa already discussed, egress is a big challenge in tall buildings. One of the first things you have to do is identify your egress goals. And by that, a simple question of, do you expect to simultaneously evacuate everyone from the building? Do you expect only to evacuate certain people and keep other people remaining in place? Or do you keep everyone in place except for the floor of the fire? So Grenfell, for example, in the UK, they have a stay in place philosophy. So everyone basically was expected to stay in their homes because the compartmentation of the building was expected to keep the fire to one compartment while the fire brigade came in and did their job. But you have to decide which strategy you're going to use, because that's going to help make the determination. Do you rely completely on stairs? Do you rely on partial use of evacuation by elevators, and to what extent do you do this combination? So then you have to look at different scenarios that you're going to do and look at strategies. This building, maybe it's a little hard to see. In Hong Kong, you see these dark areas. Those are refuge floors. So in a lot of countries in very tall buildings, every certain number of stories, you need to have a floor that has no people. It's just an open space, and the idea is that people can go down to that refuge area, and you don't have to take all of them down the full height of the building. So in an 88-story building such as this, if the fire is up here, people can walk down the stairs to the refuge floor, and then they can take elevators down to the lower level. So this is one way that you can manage the issue of not being able to walk all the way down 80, 100, 150 flights of stairs. So you have to look at those options and decide what you're going to take for a strategy. And if you are going to use stairs, you have to think of the walking time, issues of counterflow. If the fire service needs to use a stair in addition to using the dedicated firefighter elevators, then you have reduced evacuation time. Here's an example of what a refuge floor looks like. It's open to the outside, it's sprinklered, there's should be no combustibles there, and it's a place where people can rest, because the other issue is fatigue, people getting tired if you're going down 100 stories, or if someone has a disability, even if it's a sprained ankle, a temporary disability, it's a way that you need to think about it. Horizontal stair transfers, in terms of coming down to a certain level and moving to another stair. It was interesting in Japan that, I may get the numbers wrong, but above 15 stories, a stair should all be continuous to the ground level. That's very challenging when you have a 100-story building. It becomes more challenging if you want to do something like stairwell pressurization. How do you pressurize an 800-meter shaft? You don't. If you pressurize it, nobody can open the door, so you don't have an exit. So this is where you have to think again about competing objectives. You can't just say, we'll do stairwell pressurization, or it has to be a continuous shaft, because it has to actually work. And so those different types of issues are required. Also, I showed earlier in one of the photos was the Petronas Towers in Kuala Lumpur. And that's a building with 2 towers with a sky bridge connecting them. And maybe I'll try to go back to that quickly, if I can find it. So the idea initially when the building was constructed was you're only going to have an event in one building. So if the fire's in here, building occupants from this tower can come, go across the bridge, and evacuate. And it makes perfect sense. However, after 9/11, when there was an impact on the Twin Towers, there was an analysis done of the building, and they ran an evacuation drill. And so people came down here and crossed, but people came down here and crossed, and you had a problem in that sky bridge. And so you have to think, if you're assuming a scenario of one event in one tower, and you have many sky bridges here, what if you had simultaneous events? Are people going to be trying to exit from opposite directions into that sky bridge? So that's a scenario you might need to think about. And as buildings get taller, that becomes a bigger issue because you have much more limited space in the building to move people. So you have to think about all these different options, and when you get to protection in place, that becomes a big issue as well. Professor Sekizawa talked about the use of elevators, both occupant use and fire service use. And I think, in my opinion, it's very difficult to design a super tall building without considering the use of elevators for occupant evacuation. One of the strategies that can be used, though, is to have people come down to a certain floor by stairs and then have elevators that can shuttle people to a lower level. So instead of thinking about evacuating everyone using the elevators, you can think about only moving a certain segment of the building to a safe floor and then be able to shuttle people from there. And then you can maybe get a more effective use and optimization of the elevators and the stair use. But there is a big concern for protecting the elevators and developing appropriate control mechanisms so that people can feel safe. In terms of the elevators have to be operational in an event if you expect people to use them. So they have to be protected against smoke ingress, they have to be protected against water coming in, perhaps from firefighting or sprinklers on an upper floor. You have to have very reliable controls. You need to have good communication. How long will people wait for an elevator before they go to a stair? Will they have some kind of an issue with people inside or outside of the elevator? You have to think about all of that and really focus on training, evacuation planning, and keeping those systems operational. A related factor, as I mentioned before, is if you're going to use these elevators, they need to be powered during an emergency. So if there's some event that occurs that takes out the main power, you need to design your building with enough emergency power supply to support the elevators in the emergency use, in addition to emergency lighting and other systems as well. Structural fire resistance, we have a number of examples of where we've had challenges in the past where if you have fire spread from one floor to another, you can have significant issues. So this first one happens to be the Windsor Tower in Madrid, Spain from 2005. This is like the first interstate bank where the fire spread externally floor to floor. This is a photo of the Faculty of Architecture building at Delft University of Technology. It was only a 13-story building, but the fire burned for about 7 hours and led to partial structural collapse because the fire burned up one side of the building, down the other, and then there was during the cooling phase on one part of the building and heating on the other, you had too much structural stress on the reinforced concrete and it ended up in collapse. So when you're doing design, you have to think about what is that movement of the fire? And it's not just the compartment of initial fire you're worrying about, it's what's the potential horizontal and vertical spread, and will you have heating and cooling effects that you have to deal with, and what kind of stress will that put on the building as well. So again, in the design, you really need to think about what your structural resistance goals are and what type of structural system you're going to have. So how will the load shift as you have a fire? Will you get appropriate load redistribution? What's going to happen to the primary structure relative to the fire? Will you have spalling? Will you have loss of fire protection over time? And so you need to think about the different scenarios that you are going to assess the building under and pick strategies that are appropriate for the resilience. One of the big challenges that I think we have with structural fire protection is that we have a significant reliance on the standard fire test. So we have in ISO and ASTM and other standards a standard design fire curve which talks about how much temperature you have increased over a particular period of time, in minutes or hours. But fire in a building doesn't know anything about the standard fire curve. It may be great for comparing products, but in reality, we have fires that may burn much hotter more quickly. We have fires that might be longer duration. We have different effects. And for example, I've done some work recently on post-earthquake fire performance. And one of the issues that you have in an earthquake is you get some damage, for example, to your fire protection system, for example, gypsum wallboard. And when you have a fire, after you have damage to that gypsum wallboard, you can get failure of a 1-hour system within 10 minutes. Because that fire rating in a furnace is based on perfect conditions. But you rarely have perfect conditions in a building, just normally over a long time, but certainly after an event like an earthquake. So if you're assuming that you have a 1-hour fire resistance and you breach that protection in 10 minutes, you're going to have a much different challenge on your hand within that building. So you need to think about what your real fire scenarios are, what type of analysis you want to do, and what your criteria are. It might be deflections in the members. It doesn't have to be full failure, but if you have a little bit of deflection and that opens a gap in the facade between the floor plate and the curtain wall to allow fire to spread, now you've created a fire spread mechanism. So the deflection of the structural system could have a significant impact on vertical fire spread. So all of these types of issues really need to be considered. Here, of course, we now have the issue with combustible exterior facades. Many buildings have things such as aluminum composite material panels, which are aluminum, zinc, magnesium, or other metals on the outside, but with a polyurethane or polyethylene core, which is combustible. And part of that is there to provide thermal insulation. And that is a result of some of the sustainability issues that we're pushing in terms of kind of a global society. And we saw about the fire at the Mandarin Oriental Hotel at the CCTV building and some in the Middle East. But we really have to think about what could happen in a building to ignite those fires. And Professor Sekizawa talked about spandrels and talked about different challenges, but you also have to look at what the height of the floor is, what the size of that ventilation opening is, because you're really looking at what is the length of flame and the extension of the flame. And the problem is you're looking at a radiant exposure to the glass. So if you don't deflect that flame far enough away and the flame goes up the side of the building, then you can still get an issue in terms of breakage of the glass, which could propagate the fire. So there's a lot that can be done with fire stop materials like we see here that can bridge the gap between the floor deck and the curtain wall that we need to look at, thinking of the size of the spandrels, but we also need to think about wind direction. So when you're thinking about your spandrel height and your other design features, where is the prevailing wind from? What are the wind effects on the building going to potentially do to your flame? So those types of issues have to be dealt with. And Grenfell may be recent, but we've known about combustible exterior facades for a long time. This is a high-rise hotel at a casino in the state of New Jersey in the US from 2003, where the fire burned up the exterior of the building. In that case, behind the facade was a concrete wall, so the fire didn't enter the building, so they got very lucky. We've seen many of the fires in the Middle East as well. And I don't know if the internet is working here, but this is one from France. So I don't think I have internet access, but if you haven't seen this fire in France, you should go onto YouTube and just search on Tall Building Fire France, because the videographer, somebody with a cell phone, happened to catch the building fire when it was just in one compartment and watch it go to the top of the building in less than a minute. And I think it's a very powerful video because unlike Grenfell or the CCTV building where you see the fire once it's fully engulfed, if you see the actual rate at which the fire can spread, then you get a very interesting understanding of what the challenge really is. So do that search on YouTube. I think you'll find it interesting. It's also a very good teaching tool. Grenfell was mentioned a few times, and the building was renovated for energy and aesthetics. And this is one of those situations where we talk about competing objectives, but if there were no need to upgrade the building for energy performance, you might not have had this issue, or if they had picked a non-combustible insulation, there might not have been an issue. But once the fire started, because there was so much combustible facade material, as well as thermal insulation under the facade material, you completely engulfed the building. And there was this issue that you had on the exterior this ACM material, aluminum composite material, then there was a airspace, and then against the wall was a combustible insulation layer. So you actually had parallel plates of combustible material, you had a ventilation shaft, and you had fire spread in between. So that's another reason that the fire was more severe than if you had just the fire on the exterior, because you had much more material involved. And then when you start to think about if you have a lot of material burning, you start to break windows, you get radiant ignition inside of the apartments in the building, and pretty soon all of the building is on fire. So again, you have to think about not only what the structural performance is, where are the window openings, how the fire might get into the building, it's all very important. Suppression systems I talked about before, thinking about different issues of do you have to put intermediate water supplies, how reliable does the piping network need to be, what are you talking about for system pressures and flows when you're at 800 or 1,000 meters. So you need some pretty strong pumps to be able to move water up there. You need to have that planned in advance. You want to have the water there and not rely on the systems during the emergency. So those are all part of the design phase issues. But we need to think about that with detection and alarm systems as well. You want to think about redundancy and survivability, especially if you have voice communication. So you're not running all of your cabling in one conduit. You have multiple communication paths. So if you lose one channel or one line, you have other options for continuing that network. Smoke control is a major issue as well, and we learned our lesson in the US in the 1980 MGM Grand Fire, where a fire in the casino level ultimately killed more than 80 people, mostly in the upper levels of the hotel because of smoke migration up the elevator shafts, stairwells, and so forth. And we've done pretty well about providing good smoke protection and compartmentation, but as you get into very tall buildings, you're getting issues of stack effect and wind effect that make it very difficult to control for pressurization and other types of systems, especially if you're looking at pressurizing shafts for evacuation. And you have different effects if you're in a cold environment where it's cold on the outside and warm on the inside, as compared to what we call reverse stack effect, where it's typically warm on the outside and cold on the inside. And that'll have a difference in terms of where you're likely to see the smoke pushed and how that's going to impact different levels of the building. I had mentioned earlier, if we're thinking about continuous shaft for evacuation and you're looking at pressurization systems to keep smoke on the fire floor and not go into the stair, that's fine, but you need to be able to open the door. Occupants have to get out. So if you have a very tall building, you might have to split that shaft. One continuous shaft will not be able to be pressurized and still be able to open the doors. So you have to think about those types of issues as well. Fire service, first responders have a number of issues. As buildings get more dense in terms of the city and get taller, it gets really hard to get access to the building with apparatus. It's also very difficult to get very high in the building with all the gear that needs to be brought in. So a lot of planning needs to be done in the building design phase to accommodate fire service needs in terms of communication centers, air filling, access for equipment, coordination with other building services, and so forth. I've already mentioned electrical reliability and standby power may be necessary. We have to deal with that, which is important. And we also have to think about buildings under construction. We can have significant fires when buildings are under construction, and when the fire protection is not in place, then your failure potential is much higher. So what is the plan for protection during construction? Is there water supply on site? Is there a hydrant system or a riser system for the fire department? Is there a partial sprinkler system? You can't think about waiting till the building is completed. You have to stage that fire protection. Otherwise, you could have a very serious problem in a fire that you're not going to be able to fight. One of the last things that we really need to think about is test, inspection, and maintenance, fire safety management of the building. We need much more reliable systems when you have these cities in a building, and so you have to have very good operations and maintenance manual, inspection, test, and maintenance cycles, reporting like I talked this morning about the warrant of fitness to make sure that everybody understands their responsibility with safety management in buildings. And before the building is even occupied, you have to make sure that you test all the systems. So in the past, people only did a representative sample of smoke detectors and different systems to make sure they work. But if you have this complex network of smoke detectors, activating pressurization systems, recalling elevators, and doing all of these other functions, you need to test that every system is working appropriately so that a fire on the 47th floor doesn't send the elevator to the wrong location. So it becomes very important to really think about those issues. So finally, the last point in the SFP guide is we knew the guide couldn't cover everything, but there's a lot of resources that are identified to help address some of the issues of reliability, egress analysis, and other issues appropriate to tall buildings. So with that, I just want to thank a few of the people that contributed to this, including all the people that were on the Committee on Tall Buildings, Peter Wisemantle, who is Director of Super Tall Building Technology for Adrian Smith and Gordon Gill. They were the architects of the Burj Khalifa, so getting a lot of knowledge from them on some of the challenges was very good. And I thank again Professor Ono and the organizers for inviting me and allowing me to take up some of your time today. So thank you very much.